Welcome, everybody. Thanks for showing up. I'm going to talk a little bit about Filecoin actors for the next hour. Filecoin actors they're an interesting piece of the system to try to understand. In some way, they're kind of at the heart of Filecoin. They're also something that's going to change a lot in the coming year or two. There's a pretty big tectonic shift, which I'm going to try to cover here. So hopefully you'll be kind of ahead in thinking about not just what the network is, but where the network's going with this talk. So when I threw this together last year, I subtitled it "Dumb Contracts for a Smart Network," which is still kind of true. But you'll see as we go on, it's actually transitioning to something more like smart contracts for a smart network. Okay, so we're going to answer 3 questions in the talk. What are Filecoin actors? Why do they exist? And what are they going to look like in the future? And the first question, the answer is pretty simple. They're hard-coded programs that run on the Filecoin blockchain. So if you understand Ethereum-style smart contracts, you more or less understand Filecoin actors. They are written ahead of time by protocol engineers in the current moment in order to make the protocol work, which we'll get into in the second section a bit more. But first, because we have people maybe coming from backgrounds that are not necessarily super blockchain embedded, I'm going to start right at the beginning and get to the actor model, how it interacts with the Filecoin protocol straight up from blockchain consensus. So blockchain consensus, as I'm guessing most of you are aware of, is a way to figure out some kind of shared state using this incremental block append sort of thing. So you see a bunch of blocks, some forks where we're not exactly sure, what's real if we don't have a consensus protocol, because there's a bunch of different possible heads. But the way that blockchain consensus works is it finds the best path through a tree of possible blocks like that. So the question for us is what exactly does this path mean? And in all blockchains, it's a way to figure out what the shared state of the system is. So how does state and a path through a tree of blocks interact? Well, you have a state defined at each block. And we're going to keep a simple example in mind. So all blockchains share the problem of dealing with payments and fund allocation. So let's assume a simple state here where we have 3 addresses, F1000, F42, F900, each with different allocations of Filecoin. So the path through the blockchain actually represents state transitions over the original state. So that when we get to the end of the head, we get to a final state transition, a final state, which is agreed upon by all participants in the network. So for example, maybe we have a message which sends from F900 to F1000, 1 Filecoin. And then this guy also sends 1 Filecoin to F42. So if we sum up in some sense, or if we finish out these state transitions over these accounts, then we end up 900 sends 1 to 1,000, 1,000 sends 1 to 42, and we end up with 1199. So that's that makes sense. It's working well, and this is how blockchain payments work. And so we have these state transitions which are associated with a block, and we have a starting state and we have an ending state. So Filecoin actors are how we organize these state transitions. There's an internal state machine to Filecoin, and the entry point comes through the blocks. So to just dive a little bit into the details of how the state machine is connected to the blocks in the blockchain, we need to look a little bit at what blocks look like. So blocks are made up of really 2 things. So there's some inline data. For example, like the current height of the block, it's count in the total history of blocks, and some other things. But the 2 things that we're most interested in today are hash pointers, or CIDs. So you're probably all pretty familiar with the concept of a hash pointer, but a pretty quick redux. when you have a collision-resistant hash function, you can be sure that the data that it references is unique in some sense. And so if you have the data that goes along with it, you can have a good guarantee that you're looking at the same thing as long as it hashes to the hash that you're looking at. So you can kind of fill in the blanks, and in this sense, you have a pointer to things. Yeah, and so the two main pointers in the block header and the two that we're going to focus on today are really the big one is the state tree pointer, which points to the global state of the Filecoin network. And I'll talk about what exactly that is and how it connects to actors. And then there's also the messages pointer, which points to the messages in a block. Okay. Oops. Good. Yeah, so if you look at the state tree pointer, it points to basically a giant global map of every actor in the system. And so this is where we start to get into what an actor is. So if we go back to the payments example, so F1000, F42, and F900 would all be actors. They're all entities on the blockchain associated with some amount of funds. Yeah. Now, the messages, which you see on the right, are state transitions. So they're logical changes from the state. And every block contains some amount of messages which transition the state from the state before the block to the state after the block. And that, if we go back to the state, to the payments thing, each message is what is actually causing the transition of, like, let's send one Filecoin here, let's send one Filecoin here. And at the end, the state will be encoded. The new state is encoded somewhere in the state tree pointer among the actors. So let's dive a little bit more into the individual things we see at the bottom of the trees. So you see the triangles I'm trying to represent, that we have some Merkle tree, which is making some kind of efficient map over these things, as in it's all like hash pointed. But let's look at these leaf level objects inside of these two things. So the actor is kind of the focus of today's talk. These are objects in the state machine, and I can actually very quickly and succinctly describe like the exact bytes for you right here. There's like only 4 things in the top level actor in the Filecoin state machine model, and that's there's a Filecoin balance, which is something that we kind of recognize from the payments example. There's also a nonce, which is like this typical thing you do for replay attacks across the board in all blockchains. And then there are these 2 things which really get to the heart of the actor being a program which is running on the Filecoin blockchain. So there's a CID pointer to actor code, so the code that's actually executing because the actor is a program. And then there's also a CID pointer to actor state. And actor state is defined by the actor itself. So you can write whatever you want in there as an actor, and you get control over what bytes you write. And at the end of the day, everything is compressed into the CID pointer. Yeah, and then the block message, a little bit less important for our talk today, but it's important to understand how these things change. The block message is pretty much a transaction and regular blockchain parlance. So there's like a to and a from addressing actors that the message is going to be sent from and sent to. And then there's a target method to call on the actor because actor code, as we'll get into, is organized into methods because it's a nice like modular state machine design. And then the block message also, because it's coming from outside the system, has a cryptographic signature and it has fill value to transfer. Yeah, that's about all I'll say about messages. So yeah, here's just a little blow up. So I like to visualize like what's going on. So in terms of like the fully reachable graph underneath each pointer in the actor state. So the actor is just these 4 fields. 2 of them just totally stop right there. There's a nonce, and then there's the Filecoin inside of the actor. And the code pointer is fairly simple. So up until recently, this was kind of faked out, or definitely faked out. After the latest upgrade last week, we now have actual code being pointed to under the code pointer, which is pretty exciting. So I can make this slide, and it's like consistent and easier to understand. The state pointer contains the state, as I've kind of gotten onto, and I'm trying to demonstrate with the picture here that you can kind of put whatever weird shape in there. And in fact, you do see like just kind of emergently, not chaotic, but like there's not a one particular shape of state actors because they're programs, they make their state look the way that is best for them to use. So it looks like a bit of a jumbled mess until you understand the code and what's happening. Okay, so just diving a little bit into actor code. So again, we can lean on the idea of Ethereum smart contracts or smart contracts in any blockchain to a pretty decent extent. Actor code leaning on Ethereum smart contracts to understand. It's like you have code which runs, everyone who's validating a block is running these state transitions started by these messages. And from the perspective of an actor, it has code which is separated into a bunch of different methods in a kind of classic state machine style. And actor code is, thinking about it from a high level, there's a pretty simple paradigm. So it takes in every method, and an actor takes in parameters passed to it from a caller. So in the payment example earlier, the message that comes in is like, send, maybe that's not the best one to jump into, but you could imagine it's like, hey, this is the amount of Filecoin to send coming in through the caller parameter. But the other thing that the actor methods take in is a runtime, which allows them to interact with the rest of the system. That's their window to the outside world. And I'm trying to demonstrate that in this little graphic to the right. What an actor does can't really impact anything else or can't learn about anything else in the system unless it goes through the runtime. And the runtime has a few key things. So there's like general blockchain state that it can get. There's no writes, just reads like, okay, what's the current epoch? What's the like random beacon at this epoch? What's my balance? These sort of things that are not directly under the actor's state. There's also methods for reading and writing the state underneath the actor's state CID, which is pretty important for persisting changes. And there's also cryptographic verifying signatures and a variety of storage proofs, which is pretty important, but also pretty simple. It's kind of like a Boolean yes, no, is this proof valid? And then the one that we'll dive into a little bit more is sending, which is how actors interact with each other. So this, again, models the Ethereum send thing pretty closely. Not an expert in Ethereum, so I'm not sure if it's exactly the same, but it's the same, definitely the same in spirit. You say, this is an actor I want to send to, this is the method I want to call on it, and these are the parameters to pass in, and here's some funds. And then that will kick off a series of calls. Maybe it'll just end with that actor running its method. That actor might send more messages to more actors. Eventually, at the end of the day, everything will run, and you'll get an exit code and a return value back. If there's a failure, then things propagate in a certain way, but we won't get too much into that. One last thing, it's not on here, but there is a gas model. Again, classic smart contract stuff here. We can't allow people to just run as long as they want because blocks have a limit for how long they can be processed, and all these transactions or all these messages and state transitions are happening inside a block. So there's a gas model which charges, and that is, again, just classic blockchain smart contract. Nothing surprising in the Filecoin gas model. So that's actor code. And let me see onto, so just a little bit more about message sending. So there's like I'm trying to represent a little call graph here. All these state transitions, they start when a message is processed in a block. That's something we've covered a bit. And any change to the Filecoin state happens by some cascading of messages calling to actors changing their state, saving their state, maybe calling other actors, and so on. Messages are sent to a method. That's kind of where the methods show up when you're trying to understand the system. And I guess it's important to reiterate that actors are responsible for their own state. So we have a nice segregation between different actors. So there's good security benefits to that. It's easy to reason about. Like only an actor will be able to modify its state. and even read its state. Yeah, okay. And this is just a schematic, like, I don't know, maybe there's a good example of this showing up in the world. Like I send, maybe they get a bit complicated. I guess when you send like a proof commit message to prove a sector, you have to go off to the market actor to tell the market, hey, I'm proving a sector with like this deal ID, yada yada. But yeah, no obvious. Yeah, I think we should maybe focus on the specific part of the system in the next section. Yeah, and so here's our second question to answer today. So great, we talked. Yeah, totally.
One of the things you mentioned was that each of the actors have a fill balance. What does it mean for multiple actors within the same miner to have its own fill balance?
Okay, beautiful. So when you say multiple actors within the same miner, that's, I think, where our first point of confusion might be. So yeah, so that there is only one. So each. Yeah, I'm actually curious. What do you mean by that? Like when you say one miner, are you talking about like a miner actor, or you're talking about like a mining operation with multiple actors around it?
My understanding was like more so the latter. Maybe I'm incorrect in my understanding. So I always thought that you mentioned that an actor is basically like an object which goes through certain state transitions via some messages, and then it can send messages to other actors who then go through more state transitions.
Totally, yes.
And so if you have like a markets actor and then like, I guess, a proofs actor and then a miner actor, these are, I assume, like all interacting with each other.
Yes. And I think your question was like, what are the implications of having separate Filecoin balances per actor, right?
Right.
Yeah, I guess so. And maybe are you like in particular thinking of like, I run a mining operation, I have like several different actors on chain, and I need to like manage the funds for those different actors?
Yeah, I guess like if I'm running a mining operation, I would normally at least from what I would think, I would have a single source of funds. So what does it mean that each actor needs to have the funds in its own state?
Yeah. Okay, great. Yeah. So like it's a good question. I think that, so I don't know the specifics of how, like, I don't know like the distribution of different ways that people handle like fund management with mining operations. There is like getting into some of the details of like the way that the storage provider setup works. There's a decent amount of indirection where like in particular, the storage provider actor delegates to a set of different controlling addresses, which are typically responsible for holding on to funds, which are going to be used for transacting or adding in new funds to the system. So that's like, I guess, one answer. Like we have actors, we have actors which are around for fund management. There is, I guess, some complexity in making sure that you have the right amount of funds at the right time so that you can process transactions, process messages, which do important things. And this is, I think, a big part of like the difficulty of engineering Lotus. There's like some complexity, and that's like one piece of complexity. Yeah, I think we can get into some more later. I'm not sure I've fully answered it. But yeah, we'll move on and maybe we can talk a bit more towards the end. Okay.
Sounds good.
Okay. Well, yeah, great. So that was maybe, I'll try to force a segue. So that was maybe an example of how Filecoin is complicated. But the answer to why does Filecoin have actors is because Filecoin is complicated. So like we saw our first example of payments where you just send funds from one actor to another. And you might think like, why do we need a like whole state machine model with like different methods and many different like sorts of actors potentially in order to enable that? Like you could just do something a lot simpler. Like you don't need a full state machine. You could just do, like Bitcoin UTXO or like maybe something even nicer, simpler. And the other thing is like, hey, well, users aren't even programming these things. Like this is just, these are all hard coded as we described in the last example. All the code is fixed or it's like changed like during protocol upgrades. So like why have all these actors? And yeah, the answer is because Filecoin is complicated. So it turns out like a shared set of state transitions, and like these shared programs running are actually required for the network security, which we'll get into. Yeah, so there are 11 types of actors. We've got the 4, which you can make many of, storage provider, which we were just talking about a little bit in that question. Accounts, which just hold funds, multi-sigs, which similarly hold funds, but with some nice properties of many keys being able to provide certain guarantees. And then payment channels, which do payment channel sort of things. Then on the left, we have the system actor singletons, which are really in the mix for storage. And there's a storage market. There's a storage power actor keeping track of these stored bytes of every storage provider on the network. There's a fill plus actor, which deals with sending around a data cap and providing storage providers with more power if they have less data in their sectors. And then there's a reward actor, which deals with a somewhat complicated schedule for releasing Filecoin as part of the block reward. And then there's, yeah, just throwing out F099 is a kind of special account actor. Yeah, so there are 3, which I won't really get into, cron, init, and system, which are more about like the next level of like kind of supporting this, the abstractions for supporting the main application on the Filecoin blockchain of like enabling verifiable storage. They're important, but that's about all I'll say about them. Yeah, cool. So I'm going to overview what the system looks like today. So we've kind of talked about the like programming model for how actors can be put together, but we haven't talked about like what they're actually used for, and that's the point of this section. So we got these 11 actors, and the 2 main things that the current system of actors of these 11 actors is doing is providing payment to storage providers for verifiable storage. And so that's like from network to storage provider. And there's also a important but secondary flow which provides payment to providers from user clients who actually store their useful data inside of the verifiable shell of storage provider sectors. So I'm using these little stars to represent these protected assets on the Filecoin blockchain, basically like special state, which kind of gets passed around. And the flows of these different states are kind of nice for understanding the system at a very high level. And there is some interaction with the external protocol, so I can call that out there. But let me just show you, this is a very simplified version of what the Filecoin actors are doing. So the storage provider actor takes in proofs of storage, and if a storage provider in the outside world goes over their sectors, proves their storage, they more or less get storage power. And it's more complicated. There's different types of storage proofs. There's like things that can go wrong, but at a high level, like this is the flow. Storage providers bring in proofs of storage, they get storage power, the power actor accounts for it. During the block validation process, the power actor's state is read, and this allows the election, like the consensus mechanism, to give blocks randomly to the providers with the most power, or in proportion of their power, they get blocks. And then as part of block validation, these miners are rewarded. So there's like this implicit call from block validation to the reward actor, which then sends Filecoin to the storage provider actor, and the cycle kind of continues. So yeah, that is the flow of Filecoin. You can see storage comes in, and then Filecoin is transferred from reward to storage provider, and that's more or less what Filecoin is doing. It's trying to incentivize people to store. Yeah, so I'm going to talk a little bit about why actors are kind of hard. So if we had somebody, attack this proofs of storage, if they found a way to create proofs of storage which were not actually like made with real storage, but gave the impression that the provider had lots of storage, then this flow would get messed up, and we'd actually have big problems. So the provider could get, basically drain the reward actor with unearned storage, and it would get, I guess, unearned Filecoin. And then there's also a problem with the protocol because now because this is all connected together, in this virtuous cycle. It's become like an unvirtuous cycle, and now the attacker can produce more blocks than it should, and then we have like fork problems, we have double spend problems, like classic consensus failure problems. And I guess similarly, if we made a mistake in the storage provider actor because it's trusted code, this isn't the case, but if an attacker could do arbitrary things in their storage provider actor, they could, for example, ignore their proofs of storage, or I don't know, they could add an extra send to the power actor. You could imagine if someone could exploit the actor, then they could do the same sort of thing. They could get fake power. The system would read it, and the same sort of thing would happen with consensus failure and funds draining unfairly. So this is going to show up a little bit later, but yeah, it's kind of important to remember that these actors, as they are today, are on the critical path of blockchain security. So the other thing that's worth thinking about is the storage market. So this is a way to facilitate client and provider interaction for actual useful storage of data. And so clients will provide deals, and those deals will get associated with a storage provider's sector. And clients have flows of Filecoin through the market to the storage provider, assuming that they store correctly. Again, this is very simplified. The other thing that's interesting to keep in mind is that the Filecoin protocol is trusting that the Fil plus actors, verifiers, and top level root key are good. And then this Fil plus actor actually sends in this data cap, which allows Filecoin data to be valued at 10 times the value of non-verified data, which means that if we go to the next slide, you get a connection between the Fil plus actor and the power actor, because power is created from a combination of this blessing of verified data and the actual storage. And to belabor that point a little bit, if you have a sector that is packed full of deals which have been verified by the Fil plus system, then you actually get 10 times the power for that sector than if you just had regular deals or if you had nothing at all. And this is a nice, again, simplified schematic of how these things interact and what the system looks like. Just quickly again, if there's a problem somewhere on the market actor or the Fil plus actor, you have potentially a massive problem. So this again is on the critical path for blockchain security. And then payments are kind of simple. They're not really involved with this critical path. They're just able to send funds between anybody. They are quite important. A lot of users rely on their multi-sigs to be secure to do things. Exchanges would be very unhappy if multi-sigs were no good, but they have a different property. They're kind of more free floating, which is somewhat of a transition to the next and final question. So what are these actors going to look like in the future? And the answer I have for that is, so this is definitely less decided. It's not real yet. It's still the future, but the way that it seems like this is going to shake out is we will have two layers. We're going to have system actors, which more or less correspond to what I've been talking about so far. And then there's also going to be user space actors, which are new and exciting. So in order to motivate, at least from the actor perspective, the transition that's happening and how nice it's going to be, I want to talk a little bit about how actors have changed since mainnet. So there have been, a decent amount of things. So we've done this thing called Snark Pack, optimistic window post, snap deals, as well as a bunch of security fixes and small improvements, optimizations. And that's been good. And we've gotten, I think a pretty decent amount of value added to the protocol by making these changes. Lots of cost reduction and some new pretty great features. But it's been, almost 2 years, it's been a year and a half. So why haven't we done more? And so this is where we kind of get back to that critical security path. So in order to make a change right now to the system actors or to any actors at all, there is a process of sending out a spec to the broad community, which is called a FIP, which is essentially the same thing as an EIP or a BIP. It's a Filecoin improvement proposal, and it requires a lot of work to get this idea out, gather some sort of consensus, and think things through. Part of the reason it takes so long and we want this sort of slowdown is because of the security constraints, right? Like we saw, there's potentially really bad things that happen if we make an error in the main system actors. So yeah, that's part of it. It's also because like these things are critical to the protocol, so we want a lot of community buy-in before we really do anything. Like there's an inherent slowness to governance, and so yeah, that keeps FIPS being slow. The other big thing is that any change to the actors is right now requires a network upgrade for the consensus protocol to work at all, because actors are embedded in the consensus protocol. If you want to change more or less anything, then you need to everyone needs to agree about that upfront beforehand. So what that means is we need to do what we call a network upgrade, which is basically like a friendly name for a fork, which is good because we should expect changes, but it's also hard and it requires a lot of upfront costs and a lot of testing, a lot of communication. It's just inherently slow. So these things together bring down the velocity of actors changes. And then of course there's the added maintenance costs. Any new actor, any new code needs to be maintained, which is potentially non-trivial. And the result is that it's hard to become a contributor. You have to have a lot of context. You have to understand the protocol very well. It's hard to decouple changes because everything is kind of tied together, and you don't want to mess up something in a far-reaching part of the system by changing something close by. So even if you have a good plan and a good team, it's always going to take time. And that's more or less the way it has to be. So here's an example. I won't go into the details too much, but yeah, and we started snap deals, which is a way to quickly add in data to a sector which doesn't have data, which is a pretty great idea. And there's some very clever construction. We started thinking about it in July and took till March until we actually got this in the network live for people to use, which is, I think was pretty good, but it took a lot of time. And I guess to reiterate how these changes can be difficult, like here are two bugs which showed up during Snapdeal's actors development. So one I found before things got too far. So in October October of 21, it turned out that a naive implementation of the Snapdeal's change in actors would basically let anybody slash anyone who was using Snapdeals because we weren't correctly figuring out how to write the minor actor. Which would have led to, exactly the situation where it was a bit different than what we talked about before, but kind of like the inverse direction. And an attacker could remove the power of other storage providers and, maybe cause a decent amount of havoc. So that would have been a pretty bad bug to get in. And then also, even though we worked hard and did a bunch of testing and moved, slow enough to try to be safe, we actually introduced a bug into actors on the upgrade, which we only found the day after we threw it in. It turned out that wasn't a big deal, but it pretty easily could have been a big deal. So even when we're working as robustly as we can, like mistakes still slip through. And that's like the maintenance cost. We have to potentially re-upgrade something like that if something really bad happens. And yeah, no need to understand the details here. I went over that very fast, or even like how it connects, but basically just the idea that like the critical path for blockchain security is part of the reason for the slowness of development. That's really what I'm trying to get across. Okay. Sweet. So now we're going to talk about the FVM. Everyone's talking about the FVM. It's new and exciting, but it's also potentially very valuable. And yeah, I think it's pretty easy to see that as someone who's been writing actor code for the past couple of years. So like what the FVM means is basically no FIPS and no network upgrades. So users can write new actors. They're going to be separated enough from the core like system actors that it's not going to be as security critical to develop them. So they should be, assuming that we do things right, decoupled enough that this whole like awareness of the entire protocol is not a requirement for writing them. And also they should be deployable at any point, just like in, say, Ethereum or any other regular smart contract platform. You can just throw up a new contract. So you can throw up a new actor without a network upgrade, which also means you'd no big slowdown in that from that perspective. So this all results in a lower barrier to contribute. So no FIT process, open network. It also means, yeah, because of the way that we're doing things, there's familiar technology backing this stuff up. So that's pretty nice. And ideally, though, of course, some contracts are going to, or some actors are going to want some more deep knowledge of the Filecoin protocol. It probably won't be as required. And it still is going to take time to write robust smart contract applications, but hey, it can be parallelized because hopefully things should be much more decoupled than actually writing them with the whole Filecoin protocol in your head. So yeah, so like, I guess a couple of visions for what this is going to look like. And this is the part of the talk where I kind of go off the rails, getting excited about the future. So take it all with a large grain of salt. So you see below the like system actors doing their crazy thing, keeping the protocol going. And one potential thing that you could imagine and will probably happen is that there will be user actors which don't care too much about the Filecoin protocol and will just do their own thing. Just talk to themselves more or less. You know, maybe they'll use like multi-sigs or accounts. Well, they'll probably use accounts for sure, but basically they won't interact with the core storage functionality of Filecoin. Like, you know, maybe it's like somebody throws a CryptoKitties clone on there or something. That's kind of the idea. You could have any of these things which are running on these other smart contract blockchains running on Filecoin. And, you know, maybe that's like pretty good because Filecoin is a useful proof of work system. So you have some pretty interesting security properties and you have some interesting fairness properties. But yeah, I don't know. I think that, at least from my perspective, what is really interesting about the FVM and programming Filecoin is that the Filecoin network has a totally new functionality, which is verifiable storage embedded into the model. So one thing that you hear people talk about a decent amount is the concept of a data DAO. So basically like a DAO as in the usual DAO, but it manages the preservation of data inside of Filecoin sectors. We don't really have time to dig into how that works, but more or less you can kind of figure out like it's going to need to interact with storage providers somehow. Maybe interact with like the power actor, maybe interact with like the fill plus actor, the market actor probably, but there's going to be some interaction with the rest of the system. And the same thing goes for other applications, which seem to make a lot of sense. So like storage providers, need capital because as Filecoin is complicated, it turns out you need to stake some funds in order to get certain security gains for the core protocol. So one thing which people have been working on is like actually like creating legal frameworks and like business agreements for lending. It could be quite interesting to do some basic DeFi stuff and pool user funds automatically into lending actors, which talk to storage providers and, deal with defaults and things like this. So yeah, that also is going to need to talk to storage providers. So this kind of the arrow pointing between the system actors and the user actors is definitely what I'm really interested in. So I think what we kind of end up with is this like nice layering. So you have user actors and system actors, and I think that so it is an active area of design and thinking to try to come up with like a good API abstraction to make sure that we do this right and we expose the right things. There's also a lot of work about to kick off, which refactors the system actors in a way that it might be easier for user actors to call into them and get the right sort of functionalities. Basically this is like, this is what I'm thinking it will look like. And I guess a key thing I'm bringing up here is that the user actor is always going to kick off the interaction because the system actor needs to not know about or care about them. It has its own, like the system has its own job to do. I guess the OS like analogy is like maybe not so bad you have this like system which is taking care of important things that the user does not care about, like, you know, making sure that your drivers are working like between your machine and your monitor, or like making sure that your power supply management. I don't know much about operating systems, but like there's important things which the system is doing. But then it also allows users to get resources from that system in a way which allows them to build great applications. And I think that's the direction that these two, that the FVM and actors collision is going to send itself off into. And this is the part where I go really off the rails. So like, I think that there's a lot of things that can be done, and it's not just me. Like a lot of people at Protocol Labs and, you know, outside of Protocol Labs are excited about the stuff you can do. And there's a lot of different things I could have thrown up here, but this is just like one potential synergy. So there's this group at Protocol Labs called Consensus Lab, and they're basically working on like sharding with a particular sort of like rollup actor. A rollup actor, as I'm trying to demonstrate here, it has as a state pointer a whole other state tree, has like a whole other network. And the idea is that all of the message validation stuff happens off chain, and then like there's some sort of delegation of disputes to the main chain. So that's like something with an FVM, you can pretty easily just create these guys in user space. And another thing, I've got another link here. The CryptoNet team is working on what they're terming a retrieval pinning service, which is basically a way to guarantee somehow that data that you store with someone can be retrieved back. I don't claim to have any idea how it works, but definitely an interesting idea. And I'm pretty sure their plan is to use a series of user-defined actors interacting with the system to achieve this goal. And then, just like a few, like, I don't know, a few hours of thought, you can start to like put things together. So like a wild speculation when it comes to blockchain sharding, like the data availability problem is, I'm not a sharding expert, but as far as I understand it, like being able to guarantee that data is available is a big bottleneck in getting like proper security for blockchain shards, because when you want to do these like delegated fraud proofs, you kind of need to get the state underneath the rollup actor. So like big question mark, like maybe you could like throw these two things together, and maybe we could have like a really good answer to, or like a starting good answer to a major problem, which is like blockchain sharding. So that's like, and I guess like there's many other paths you can take, which is why I'm excited about the FVM. I'm excited about actors rolling into the future, and I think you should be too.